How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for trends of the periodic table. And you can see here I kind of made a little cheat sheet for what those trends are. We got ionization energy, which increases going to the right across a period, as well as towards the top of any group. Electron affinity, doing the same kind of pattern, becomes more negative as we go left to right or towards the top. And atomic radii, which does kind of the exact opposite. It is greatest to the left and towards the bottom. All right, so let's see how we can apply that knowledge to some of these questions. What does the atomic radius of main group elements generally, I'm sorry, that shouldn't say what, it should say why. Why does the atomic radius of main group elements generally increase as you go down a group? Well, as we go down a group, well, let's say we got hydrogen and then we got lithium, which has, oh, hey, wait a minute, it's got 2 energy levels. And if we keep going, we add more and more principal energy shells as we go down a group. So more energy levels or principal energy levels is why it gets bigger. It's like adding more layers onto an onion, right? It's going to get bigger. Number 2, put the following in order of atomic radius from largest to smallest. So let's see what elements we're talking about first. We got argon. All right, where did my pen go? Here we go. We got argon and magnesium. So over here, we got sodium, we got phosphorus, and we got silicon right there. Oh, hey, look, they're all in the same period. And as we go left to right, the radius gets smaller, right? Because we have the same energy level, but we are increasing the positive charge in the nucleus. So there's the same amount of shielding, but the nucleus is becoming more and more positive, which is pulling those electrons in closer to the nucleus. So if we want from largest to smallest, the largest one's going to be the one on the right. So we're going to go argon is larger than phosphorus, which is larger than silicon, which is larger than magnesium, which is larger than sodium, right? So that would be the order from largest to smallest. Number 3, which of the following would you expect to have the largest atomic radius? So here we go. We got oxygen, fluorine, sulfur, and chlorine, and they're all kind of clustered together right here. So we know for atomic radius, it's biggest when we go to the left and we go down. Right to the left, we have lower effective nuclear charge, which means those electrons won't be held as closely. And as we go down, we have more layers. So which one would you expect to have the largest one? To the left and to the bottom, sulfur. There you go. 4, explain why the following is an isoelectronic series. If you've seen iso before, that means same. So isoelectronic, we're talking about the same electronic structure. So if we see oxygen here, it has a basic configuration of 2-6. 2 electrons in the first energy level, 6 in the second. But this -2 means, hey, it gained 2 more. So it's really 2-8 for the O-2. F- was 2-7, but that minus means we gained 1 more electron, so that makes it 2-8. Neon is 2-8, and sodium, where's sodium? Sodium was 2-8-1 with its 11 electrons. How did it become positively charged? Where's my pen? Positively charged. It lost that 1 electron. So that's why they have the same, why they're isoelectronic. They all have 2-8, or if you want to go quantum, 1s2, 2s2, 2p6 for their configuration. 5, arrange the following in order of increasing atomic radius. Hey, wait a minute, they're using the same elements as before. So we know that they're all 2-8 from the previous problem. But if we take a look at oxygen, it has a +8 nuclear charge, fluorine has a +9 nuclear charge, neon +10, and sodium is +11, because that's the atomic number. There's 11 protons in there. The nuclear charge is +11. So they have the same electron configuration, but the nucleus has different charges. So let's say, all right, if we want to go increasing atomic radius, which one's going to be the smallest? The smallest one is going to be the one with the biggest nuclear charge. So the smallest one is going to be that sodium ion, Na+. The second biggest one would be neon. The third biggest one would be that fluoride ion, and then we have the oxygen ion, the oxide. So the biggest one, or the smallest one, Na+, Ne, F-, O2-, right? So smallest to biggest, there we go. 6, which of the following would you expect to have the largest first ionization energy? So we're looking at, again, these 4 elements that are kind of grouped together on the periodic table like this. First ionization energy. What is the pattern for that? Oh, sorry. Largest first ionization energy. So ionization energy, how much energy it takes to remove an electron, increases as we go left to right, as well as bottom to top. So we're looking for elements that are further to the right and towards the top. Chlorine. The reason chlorine has the highest ionization energy is because it's holding on to those electrons the strongest. So it's going to be the hardest to remove them. All right, 7. Which group on the periodic table has the lowest first ionization energy? So which one of these is the easiest to remove an electron? Well, that would have to be our group 1. Those group 1 metals are so reactive that you won't find the metallic version of them in nature at all. They've reacted, they've oxidized, something has taken electrons from them. They're the easiest elements to remove electrons from. Which of the following equations represents the first ionization energy of aluminum? So first ionization of aluminum, so I know I'm starting with aluminum, and if it's the first ionization energy, it started as aluminum 0, had no charge, and then ionization is removing an electron, so it separated an electron from that, giving you the +1 charge. Now, first ionization has to happen in the gas phase. That's part of the definition for first ionization energy. So it's an atom in the gas phase. So which one of these options is it? I think it looks like it's choice D. So there you go. All right, number 9, which of the following equations represents the second ionization energy of calcium? So again, ionization energy has to be in the gas phase and just a single atom. And if it's the second one, this has already happened once, so calcium's got a +1 charge. Ionization is removing an electron, and that means that its oxidation state, its charge goes up an additional 1, and it's still in the gas phase. So which option is that? It looks like choice B. All right. Which of the following elements would you expect to have the most negative electron affinity? So when atoms gain electrons, they release energy. Which one of these will release the most energy? Well, let's see. We got sodium, we got lithium, we got beryllium, we got nitrogen, and we got fluorine. So ionization energy. Oh, I'm sorry. No, electron affinity becomes more negative as you go left to right and towards bottom to top. So which one of these options would it be? Definitely have to be fluorine, right? Fluorine's going to have the most negative electron affinity out of those options. All right, 11. Which of the following elements has the most negative electron affinity? Again, electron affinity becomes more negative as we go left to right, as well as bottom to top in a group. So let's see what elements we got. We got aluminum, we got silicon, we got phosphorus, we got boron, and we got chlorine. Interesting, interesting. All right, so if we think about this, maybe you got it tied between boron and chlorine because, boron's towards the top, but chlorine is more to the right. Now here is something to think about. We know that chlorine is a nonmetal, boron is a metalloid. We know that nonmetals like to gain electrons. So which one is more likely to gain electrons between boron and chlorine? It's going to be chlorine. Chlorine of those options is going to be the most negative electron affinity. For number 12, which of the following accurately represents the electron affinity of bromine? So again, remember that electron affinity is for just one atom, and it has to be in the gas state. We know bromine is one of those Brinkelhoffs. It is a diatomic molecule, but that can't be true for electron affinity. Electron affinity is an atom in its gaseous state gaining an electron. So we got to start with bromine, just one, in the gaseous state, gaining one electron to become, well, what happens to that? Now the bromine becomes a negatively charged ion. So which one of these options shows that? Option A. All right, number 13. In general, as you go across a period in the periodic table of elements, left to right, the atomic radius, well, we know atomic radius left to right decreases. The electron affinity becomes, left to right, becomes more negative. And the first ionization energy also becomes greater. So which one of these options fits the bill? Well, let's see. Looks like option A, decreases, becomes increasingly negative, and increases in energy. Awesome. I think that might be the only option. Let's see, decreases, nope. Decreases, yes. Becomes decreasingly negative, no. C, increases, no, I'm sorry, like atomic radius doesn't increase. Let's see, atomic radius decreases going left to right, yes. Becomes increasingly negative, and then decreases, no. So best option is option A. And I think that's it for this section. I hope you found it helpful. If not, I'll see you in class. Okay, bye.